In this video, we're going to look at question 3 from the torsion section of the course notes. So that's on page 51. The question is, a solid steel shaft is required to transmit 80 kilowatts of power at a speed of 300 revolutions per minute with an angle of twist not exceeding 0.5 degrees over a 4 meter length. G is given is 70 giganewtons per meter squared, and we're asked to determine the minimum diameter required. We're going to have a think about which of our equations we need to use here. Always in these types of problems going to be using our equation for torsion. So we'll write it out here, where we have torque over polar second moment of area is equal to tau divided by r, our radius, and that's equal to g theta over L. So we have all of the components that in our equation there, and we've got to think about what we can use to get the information that we need in this question. So let's have a look. In the question, we know we have been given G, we've been given theta, and we've been given L. So we've got everything in this part of the equation, we can use that. But we haven't actually been told the torque or the shear stress or the polar second moment of area, which we can't find J because we're trying to find diameter, and we don't have R either because that's what we find the diameter. So how can we find out some more information? Well, we have some other information in this question. We're given the power and the angular velocity, and we also have this equation here. Power is equal to omega, the angular velocity, times the torque. So we have a way of finding this. So how does this help us? Well, if we've got the torque, and we've got everything in the green circle here, it allows us to find J, and J we can use to find the diameter. So we'll use our other equation we use in this part of the course. We'll have that J is equal to pi d to the power 4 divided by 32, and D is the thing we want to find. So we'll work through all of these steps, but we're going to use the power formula to find torque. We have power and angular velocity, with torque one time. We're going to find torque. We use torque to find polar second moment of area, and we use polar second moment of area to find the diameter. And sometimes it's not obvious in the question how we're going to do this. So let's take this from the start and think about how we would go about solving this question. So that's the approach we're going to take, but let's take it from the question. The first thing to do in any question like this, where we've got lots of values given to us, is start to write them all down. So I'll make a list of them here. So we're given power is equal to 80 kilowatts. Angular velocity is equal to 300 revolutions per minute. The angle of twist, the maximum angle of twist we're allowed, call this theta max, just to remind me, is 0.5 degrees. The length of the shaft is 4 meters, and our value for G is 70 giganewtons per meter squared. And just a reminder, G is the modulus of rigidity. That's a property of the material of the shaft. This is the information that we have. So we know to use our formula for torsion. We need to work out, first of all, what the torque is. That's the clue, is that we've been given power and angular velocity, because the two of them combined, the only purpose they can serve us in this type of problem is to tell us the torque. So we start off by using this formula here. So power is 80 kilowatts. So let's again put these things into the type of units we use. So we'll be using watts for all of this. So 80 kilowatts, well, that's 80,000 watts. Our angular velocity is in revolutions per minute, but we want it in radians per second. So what we have to do is convert this. I'll do it at the bottom here for a wee bit more space. So we want to replace revolutions with radians. Put radians at the top and revolutions at the bottom here, because revolutions on top will cancel out. So 2 pi radians is equal to 1 revolution. So that will transform our units into radians. But we also want it per second as well. We want seconds in the bottom, whereas minutes are minutes in the top to cancel that out. And 1 minute is equal to 60 seconds. So to get our angular velocity converted into radians per second, we're going to multiply by 2 pi, that comes from converting revolutions to radians, and divide by 60, which comes from converting minutes to seconds, as in per minute to per second. If we put that into our calculator, we actually get 31.416 radians per second. So I'll write this up in our list of parameters. So I'm just going to rub out that just now to give it a bit of space, but I'll keep the value. We've got 31.416 radians per second. So if you want to see that again, you can just go back in the video. So we now have our units for both power and angular velocity in the units that are required for the question. So we can write that torque is equal to power divided by angular velocity. That's just dividing both sides by omega there, and put in these values. So we've got 80,000 for power, and we've got 31.416 for angular velocity. And if we put that into our calculator, we get something in the region of 2546 Newton meters, are our standard units for torque if we're working in watts and radians per second. And you might have a bit of variation there depending on the rounding that you've used for the angular velocity, but this is the value you should have for torque, 2546 Newton meters. So I'll just rub out our second moment of area equation just now to give us a bit more space. We'll come back to that later. We can now use this equation at the top of the screen because all the things that are now, all those green ticks up here at the top, we have all of them. So we don't need tau and R. We're not going to be using them just now. We don't have shear stress, and what we're trying to find is the diameter, which is twice the radius. So we can write this out like this: T over J is equal to G theta over L. We could stick our numbers straight in, or we could do a wee bit of rearranging first of all, because what we're trying to find here is J. We know G, theta, and L. We're given them in the question. And torque we've just worked out. It's J we want. So let's do a wee bit of rearrangement. So to rearrange this, we're going to have J is equal to, and we need to do a bit of multiplying across here, but J is going to be equal to LT over G theta. So effectively we've flipped these across to get J as the subject of the equation here. And now we can put in all of our values. Well, almost, because we need to make sure that these values too are in the correct units. So let's have a look at them. Well, L is in meters, that's what we want. That's exactly what it should be. Torque we already have in our correct units because we worked that out in the previous step in this question. But G and theta are not currently. G is in giganewtons per meter squared. Well, giganewtons are billion newtons, so that's simply 70 times 10 to the 9 newtons per meter squared. But to get degrees into radians, what we have to remember is that there are 2 pi radians in 360 degrees. So once round the circles, 2 pi radians or 360 degrees. So we multiply by 2 pi and divide by 360, and that gives us 0.5 degrees as radians. And it's quite a small number, but that makes sense because it's quite a small degree. And I've done this previously, so I'll just get it from my sheet. And it's 8.727 times 10 to the minus 4. Sorry, times 10 to the minus 3 radians. So now we have all 4 values we need to calculate J, our polar second area, in the correct unit. So let's put them in. So we've got L, which is 4, our torque, which is 2546, divided by G, which is 70 times 10 to the 9, times theta, which is 8.727 times 10 to the minus 3. Now, depending on how you've chosen to do some of your rounding in this question, you might have a slightly different answer from me at this point, but it should be along the lines of 1.667 times 10 to the minus 4. And remember, polar second moments of area, like second moments of area, have units of length to the power 4. And because we're working in meters throughout here, it's meters to the power 4 are our units here. So that's us got J, our polar second moment of area. And this is the second of our 3 stages. The last thing to do is to remember what our equation is for calculating J if we know the diameter. So I'm going to shift in, so I'll pull this down a wee bit and shift down slightly here. Well, we're told in the question, if I'll go back up, it's a solid steel shaft. There's 2 different equations to use for J, but for a solid steel shaft, J is equal to pi times the diameter to the power 4 divided by 32. So to get D, we need to rearrange this. What we need to do is, well, first of all, we'll rearrange for D to the power 4 is equal to 32J divided by pi. But what we're looking for here is something a little bit more complicated. We're looking at for the 4th root of J. So D equals 4th root of J, 4th root of 32J over pi. The 4th root of D gives us this. Now, this might be something you're unfamiliar with at this point, and I'm going to talk you through what I'm doing when it comes to calculating a 4th root, but we can do the bit inside the root quite easily because that's a normal calculation we're used to doing in this course. So I'll write in 4th root just now, 32 times 1.667 times 10 to the minus 4, that value coming from up here where we just worked it out. So we take that, put it in here, and divide it by pi. So we can do this calculation first before we talk about 4th roots. And that's going to give us, I'll keep writing D here, D is equal to the 4th root of 1.698 times 10 to the minus 4. Now, when it comes to doing a 4th root, it's your calculator might have a button for this or it might not. But what you can also do is to put something to the power of 1/4. So you'll have that button in your calculator with X with the box. So if you put in 1.698 times 10 to the minus 4 and then press that X with the box button and put in either brackets 1 divided by 4 or 0.25, they're both equal to 1/4, and put that in, it will do the same thing. So a 4th root is effectively to the power of 1/4, if that works out better. But please ask me to go over this in class if it's something that isn't clear. But by putting that into putting the 4th root into the calculator, what you'll get is 0.1142 meters, or if we put that in millimeters, 114.2 millimeters, which actually works out as the same answer in the course notes. Yours might vary ever so slightly because of rounding, but that's what we have aimed to get to. So using our 3 different formula that we have, the torsion formula, the power formula, and the polar second moment of area formula, we're able to solve and find the minimum diameter that is required to keep the angle of the twist at no more than 0.5 degrees.